Guys, welcome to Physical Sciences. This is one interesting and very, very life applicable subject. It's about physical sciences, and it's a combination of two subjects. It's physics and chemistry. So in grade 10 for term 1, we're going to focus more on the physics part. And our first topic, we'll be talking about waves. And when I talk about waves, I know some of you are thinking about the ocean right now, that yay, what a wave, blah, blah, blah. All right, it's part of it, and we're going to look at how it works as well in terms of waves. Now, please understand, with physics, we're going to do a lot of definitions, more like your natural science. Definitions. And I need to quickly warn you that the definitions are either you get them right or you get a 0. We're not going to give you marks for, oh, but he tried. No, you'll get a 0 if you don't define it the way it's supposed to be defined. So you need to do your physics and practice your definitions every time you study. Okay, so when we look at waves, we're thinking about different types. I think we did a bit of it in natural science grade 9, where we talk about sound waves, light waves, heat waves. I'm sure you've heard of those things. All right, so we are going to go quite deep into it this time, and we are going to start by doing some basic definitions that I need us to have. We are going to define 3 things quickly. We are going to define a pulse, we are going to define a transverse wave, and we're going to define amplitude. Remember what I told you? The definitions are so crucial that we cannot survive without them. So, definitions. We are going to start by defining a pulse. Let me divide my board into 2. Definitions. Number 1, a pulse. I'm sure you've done this at school. Do you remember what a pulse is? Yeah. What is it?
It's a disturbance in a medium that moves from one to the other.
Okay.
A single disturbance.
Yes, that's the word I'm looking for. It's not just a disturbance. A pulse is what?
A single disturbance in a
A single disturbance in a
medium.
medium. And if you write that, you're just fine. A single disturbance. It must be one disturbance in a medium. Let me try to see something here. All right, I wanted to create just, okay, let's get a pulse. Look at this, a pulse. It's one. It's just one that goes right across, right? A single disturbance. Let me increase that. A single. Can you see that? I only disturbed it once. A single disturbance. There we go. I don't know if it makes sense. So that is a pulse. A single disturbance in a medium. A single disturbance in a medium. Now, our second definition would be to define what we call a transverse pulse. So wherever I can show you a simulation, I will show you. Wherever I can show you a picture, I would also show you. All right. What is a transverse pulse? Particles.
When particles of the medium move perpendicular with the propagation, particles in the medium.
You look like you've studied your definitions very well. All right, guys, I wanted to quickly associate the word transverse with perpendicular. Keep that word in your mind. And when we say perpendicular, what do we mean? We mean at right what? Angle. So keep that at the back of your mind, that every time I talk about transverse, I'm going to have to talk about what? Something perpendicular. perpendicular. All right. So let us define a transverse what? Pulse. Now we talk about a medium. Waves must travel through a medium because this is what happens with waves. Waves transfer energy from one point to another. Hence, it requires a medium. So a medium is anything that has particles. So the way I'll show you what happens, let me try to see if I can show you. Do you see that those red dots and the green dots, those are the ones we call particles. And what happens is they transfer energy. If they are not connected, then they won't have energy transfer. That's why it must be in a medium. If it's a vacuum where there's no air, then we can't talk about waves. We cannot talk about what? Waves. Look at that again. Beautiful. Oh, I just love that. A single pulse. So energy is transferred as the waves goes on. Energy is transferred. All right, so let's look at our definition. Let's write this definition quickly. A transverse pulse is a pulse in which the particles of the medium the particles, okay, wait, there's a hand. Shifiwa, your hand is up. Shifiwa, your hand is up. Let me know. I can't hear you though. I don't know what's going on. Hayden, your hand is up. Quickly talk to me. Let me see what's going on. Okay. Are you saying something, those? Shifiwa? Type, let me see. I don't know. Is there a problem, Hayden? Wait, I don't seem to be able to hear you. Let me check something here. 1 second. Can't seem to hear you guys. Let me see. All right, my sound is fine. Let me check my... Oh, wait. Okay, I can hear you. Talk to me. I can hear you now.
I was asking if it's possible for you to send the slides on my
why? You don't want to write?
So, because I'm in the transport.
You are in there?
Transport.
Oh, okay. All right. Okay. I'll make a plan for you. Okay.
Thank you, sir.
Understood. But don't log out. Just stay on. Okay.
Yes, sir, rapidly.
All right. Okay. A pulse in which the particles of the medium, what did we say? Move perpendicular. All right. Or we can use the word what? Right what? Angles to the what? I don't want to use, I don't want to, okay, if you remember the word propagation, but just use to the direction of the motion of the pulse. Okay. But it's fine, it's the same thing.
Okay.
Motion of the pulse. So if I were to draw a diagram for you, this is what I will draw. Direction of the pulse. So you have the medium going up and down, and you have what? Direction of the pulse. You know, a good example of this is water waves. If you put a paper on water, what happens? You see the paper moving up and down. That's what we mean. Direction of the medium and direction of the pulse, and that is 90 degrees. And that's what we call a transverse pulse. Hayden, your hand was up. I'm not sure what you wanted to tell me.
It's fine. I just wanted to I'll keep you on with what you were saying, but you couldn't
Oh, okay, all right. Yeah, I noticed something was mute on my sound. All right, number 3, amplitude. Okay, let's see. There's a hand. Zoe.
Hi, sir. Also, another form of a medium is like a slinky, the toys.
A what?
A slinky.
You know, in
Like a spring.
Oh, those little rings that you. Oh, yeah. But no, that is actually. Okay, yeah. If you see it like a worm. Yeah. Okay, I get you. I think I must have something like that as well. Okay, but not here. I must have something like that as well. Okay. Yes. All right. So if you are in the lab, you would use that and you would say that beautiful, beautiful, beautiful. Okay. Our third definition, amplitude. For amplitude, we are going to use a letter A. Now, this again, we will talk about all of this when we talk about when we get to trigonometry in maths. It's kind of similar stuff. Okay? Amplitude, do you remember your definition?
Yes.
What is that?
The displacement, the maximum displacement or disturbance in the media from equilibrium.
Okay, you have to mention the word maximum. David, your hand is up. You want to tell me something?
No, sir, China, I need to answer.
Okay, no, shoot. Answer me. Answer me.
Sir, the altitude is the maximum displacement.
It's the what?
Is the maximum displacement of a particle in the medium from the equilibrium position.
All right, from the equilibrium position. Yeah, you guys are saying very lovely words. I love them. All right, I would just say it's the maximum displacement. The word maximum must be there. Or even I could use the word the maximum disturbance of a what? Particle. Maximum what? Disturbance of a particle from rest. And that rest is what you call a position of equilibrium. A maximum displacement or maximum disturbance. And we are going to repeat almost all of this definition in just a while. Maximum disturbance from its rest position or a position of what? Equilibrium. Please take note of these definitions. They are very, very key. Are we okay, everybody? Are we okay? We've got to quickly cover a few grounds. Now, I'm going to look at, I know you probably also did this. Yes, there's a hand. Any question? Can I move on? Do you know what I want to talk about now? Superposition of what? Pulses. Let me know if you need to write and I'll go back. Just trying to cover some ground. Superposition of pulses. Of pulse. Superposition. Did you understand this when you did it at school?
Not really.
Okay.
It's at the base of the amplitude.
Of two pulses.
Yeah, of two pulses that
But-
they meet of course, in the same equation.
The definition is on point. I love that. That's beautiful. All right. So we're going to define the principle of superpositioning. Let's start number 1. The principle of superposition of pulse is the algebraic. We're coming with math again. Algebraic what? Sum. So basically we are going to do what? to add. Of the amplitudes, and I need to quickly do that amplitude thing for you now. Of what? Of two or more. We could have more than one, but for now we'll use two. All right? Two pulses that occupy the same space at the same time. I want us to go back to, I know you're writing, I'll go back to the amplitude. I want to do something there quickly. I know you're writing, I want to do something again, and you might just need to just squeeze this diagram in on the amplitude. All right, I'll come back. I know you're probably writing. Our equilibrium position here is 0. That's the starting point. So if I look at the maximum of the white one, I'll have that as that. And if I look at the maximum here at this particular point, so I'll call this a positive A, and I can call this a negative A because it's below at that particular point. So we're looking at it at this point. Maximum displacement. All right. Please just quickly draw that on the amplitude. Maximum displacement from the start to the top. Because that is going to help us understand the algebraic sum. I'll give you 30 seconds to draw that. It's getting cold. Can I move to the next? Back to our superpositioning. All right, the principle of superposition of pulses is the algebraic sum of the amplitudes. I should put an S there. Of two pulses that occupy the same space at the same time. And here we have two types. And? Okay, we use the word destructive. All right. Constructive and destructive. Let's see quickly. Then I'll draw a diagram. Types. Number 1. What does constructive mean to you? No, just the general word constructive.
To build up.
Lovely. And let's use the word constructive interference. All right, the word constructive means to build up. I love that word. To build up. And the second one would be what? Destructive. So what does the word destructive mean to you?
To break down.
Interference, which means to what? To break down. Beautiful. Because that's really going to help us understand the concept. And now I'm bringing a different word, interference. What does interference mean? Good. So it's more like, already we have talked about it. Let me just put it down quickly. Interference is what? The coming together of two waves. Of two pulses. But now I want us to quickly describe our constructive, and we're going to do some maths now. Constructive interference. So already we're saying two waves are coming what? Together, or two pulses. Don't let's use the word wave now. Two pulses are coming what? together. All right. I think. I don't know if you've written constructive. Just please erase it so that let's in here. I want us to quickly do this so that it makes sense to us. A single disturbance. We have two important points here. Crest. And this point is called the trough. And you would see from the diagram, the crest is just the, and the trough becomes the lowest point. Okay, therefore, because I'm going to use those words. So this is the highest point on the graph, and this becomes the lowest point. And according to this graph, you would see that your crest would have a positive value, while your trough would have what? A negative, because it is right below the 0 mark. Let's quickly draw that. We're going to do more things like wavelength, frequency, and a lot more. But for now, I want us to take it very, very slowly, and then we can run. Once we build well, we would then start flying. So you did all of this as well, and you're still okay with it. Okay. That's nice. It means you listen in class. All right, please draw that quickly. We want to describe what constructive, destructive is, and then we'll draw diagrams to calculate. Then we can look at what a wave is. This is still a pulse. Can I move now? Thumbs up. Awesome. So let's go back now and deal with our constructive and destructive. So what is our constructive interference? What is our constructive interference? Remember we said the word constructive means to what? To build up. So it's going to be more. All right. So it's going to be a position where we talk about two crests, because then we add more. Remember we said it's the algebraic what? Sum. Okay. So we're going to write the definition as it's a phenomenon, that's just a big word, or principle, where the crest of one pulse overlaps with the crest of another. A phenomenon. Phenomenon is a principle of physics, right? Where the crest of one pulse, what did we say? Overlaps. The crest of one pulse overlaps the crest of another. One pulse overlaps the crest of another pulse. And once that happens, what happens? We are building up. And what happens to produce? To produce an increased amplitude. Absolutely. So if I have something like that, and I have, okay, this is how you would see it in a question. I'm just gonna draw a line here.
So they actually allow us to measure it.
Try there. I'll see. Yeah. I'm going to use letter A to represent this, and I'm going to use B to represent that. So we have two waves, two pulses. You can see one is moving to the left, and the other one is moving to the right. Okay, while you're drawing around. If they come together and occupy the same space at a particular point, what will my new thing be? It's going to be what? A plus B. A plus B, and that is constructive. What are we doing? To produce an increased amplitude. I don't know if this makes sense. Let's see. Give me a thumbs up if it makes sense, because we are producing more. All right, so you would see from my own diagram what happens. A is moving to the right, B is moving to the left, and then what happens at that point? They mate and produce. But what happens after that?
They separate.
They separate, and B continues with its original, and A also continues with, so B is still going that way. I see somebody's trying to raise a hand, and A continues that way. Anybody with a question there? Yes, talk to me. Who's that? Kiko, talk to me. Kiko, your hand is up. Talk to me. We can't hear if you're saying anything though. All right, if you're not sure of how the mic works, just unmute, or you may rather just what? Type. I want to see if I could get a quick question for you here. This one always comes in multiple choice, a lot. Okay, let me just continue. I'll get my questions together and then we'll be able to walk through. Now let's look at destructive. Kiko, I'm still waiting for you if you are saying anything. Let's look at destructive. What will destructive be? What would you say destructive would be?
A phenomenon that connects from one pulse to the next except for another pulse.
All right, so destroy means to break down, right? A phenomenon where the crest of one pulse overlaps with what? The trough. So I'm just changing that. Of another pulse. Now, are we still going to produce? Because this can no longer what? So we're going to say to produce a reduced what? Amplitude. Because we are breaking down, we are making smaller. Constructive, we are making what? Bigger. So our diagram automatically changes from this. It's no longer trough to crest to trough. Crest to crest, what would it be? It's going to be crest to, and you need to do a bit of maths. What would this be? Negative B. And you would need to see which one is bigger though. Alright? It's more as if you're doing your number line math. When they meet, I'll give you a moment to draw. You would notice that the B, okay, let me just do something for you here. What will this be? That's your A. And what will this be? Remember we said it is the algebraic what? Sum. So what's really going to happen at that point? This one here A minus what? B. Make sense? A minus, and my question would be, why is it moving down? Not really. Can somebody, why is my destructive interference down? Anybody? Yes, talk to me. Somebody talk to me. Why is it moving down? I see a hand. Do you notice here okay, I want to see if somebody can answer this question. Kiko, your hand has been up so many times and you're not saying anything. That hand must be painful now because it's raised up. I'm giving you a moment to say something, or maybe it's a mistake, or okay. Why is it down? You have no answer. Okay. Do you notice in this particular one the pulse amplitude? Let me say the trough amplitude thank you, is bigger in size than the crest amplitude. So what happens? The resulting amplitude is a trough. If the crest was bigger, what's going to happen? The resulting one would be what? Sorry, if it's a crest, what would happen? It will be on top. Take note of that. They want to catch you. All right? It's basically you're doing maths. Frosty. You said something, I want us to correct that. You said, I get the idea, but when we're marking, we're not going to mark ideas. Frosty said the destructive interference is more than the constructive. Now, I get the idea of you're looking at it down and you're using the word destructive interference. Destructive interference is what we get. Okay? You cannot have destructive and constructive at the same time. So destructive is what we get, and the reason why it is down is because the trough magnitude or the trough size is bigger than what? The crest size. I'm going to draw the other one. Let's draw something else. Are you done writing these notes quickly? I want us to draw the next one. I want us to draw the next one. And I just need to find one or two questions. Then we go to waves quickly. How we're moving. Physics is too nice. Do you believe that?
Yeah.
Physics is just too nice. Please write down that quickly. Physics is too nice. Okay, I'm sure you're done writing. Let's look at this one. What if I have something like this? What will this be? Let's call this positive A, right? What will this be? Let's call this negative B. This is moving this way, and this is moving that way. What are we going to have? We are going to have, we are going to have a positive one. But it's reduced, right? And what will this be? A minus B. And once that happens, what's going to happen to this one? It's going to continue in its original what? Movement and direction. And the A will also continue in its original direction. So here, I hope it makes sense that we now have a crest. Why? Because our interference is a crest. Why? The crest amplitude is bigger than the trough amplitude. Let me know if we are on the same page with that. Let me know if we are on the same page with that. All hands okay? Okay. I want to look for one question quickly from my book. I know I do have some multiple choice that I'd like to ask. So far so good, we're still fine. Awesome. Okay, now we go to waves. Let's go to waves. Let's move quickly. We're going to the real deal now. Everybody still okay? We go to waves now. We go to waves. Remember, we only defined what? Pulse. Now let's go to waves. What is waves? Waves is just multiple pulse. Pulse is singular. Waves is what? Many. Alright? So we'll define a wave as what? Multiple what? Pulses. More than one. So when we talk about a wave, we talk about more than one. Now quickly, there are two types of waves. And this is where we are going to do quite a whole number of what? Definitions. There are two types of waves, and I'm going to break it down for us. There are two types. Hopefully we'll be able to talk about, I think we'll only talk about one today, and examples. What do we have? Transverse wave. Did you talk about the second one at school yet? Longitudinal.
Yes.
Transverse waves and longitudinal waves. And an example of this one is water waves. Example of this one is what? Sound waves. So we're going to look into the two in depth. Transverse and longitudinal. Already we spoke about transverse poles. We're just going to take it from there. Everything remains the same. So quickly, I am going to zoom in into transverse. When we finish that, we have a lot of calculations to do as well. Okay, we'll then move to what? Longitudinal. But waves can be divided into two. Transverse, and we'll see the difference between the two. So let's start with our definitions. Transverse waves. Can I move to the next screen quickly? I need to run through some of these definitions. There are quite a lot. Wave, amplitude, we're going to define what? Crest, trough again. We're going to show them on the graph, period, blah, 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 in phase, out of phase, so many. Are we ready to move to the next slide? If you are still writing, give me a thumbs down. Okay, I think everyone is done. So we're looking at the two types of wave, and for now, we are going to zoom in into what? Transverse waves. Yes? And no yellow. I'm sure you were telling me, yes, we can move. All right, I want to increase my pace. Transverse waves. We are focusing on transverse waves. Please understand that waves transmit energy. Please don't ever forget that. Waves transmit what? Energy. And let's write that down there. Waves transmit energy in a medium. Waves are disturbances that transmit energy in a medium. No medium, no waves. Waves are disturbances that transmit energy in a medium. When we talk about medium, what do we mean? Yes. All right, it's a means or a pathway, all right, for particles to move. Example, water, air. Those are examples. So we talk about the medium, we talk about air because air has particles. When we talk about water particles as well. And later on we will see where waves travel faster. Do waves travel faster in water or air? Let me see. Can you guys answer that question? Let's see. What do you think? Okay, let's use sound, for example. Will sound travel faster in air or in water? I want to see all your answers. In air, okay. David, your hand is up.
So it will travel faster in water than in air.
Water, okay. Let's see. I've got one answer air. I've got one answer water. It's balanced now. Let's see more. I need more. Please type your answer in. I'd love to read these answers. Let's see. Zoe says in air. Okay. So, Frosty, what are you saying? Your hand is up. Sound will travel faster in air. Air. Everybody's saying air. Okay. David still maintains water. Okay. Can I leave this as a research? You should research. The correct answer is water. All right, very easy. Let me explain that to you quickly. If we talk about particles in a medium, for water, look at this. If I have my particles here, let's look at this. Particles. Let me do this. Okay, water, air, solid, What do you notice is the difference? Do you notice the space between them? It's like, I want you to imagine you have 10 people in a line, and you ask them to pass your pencil case. In the first one, the 10 guys are so close to each other, there's no space between them. In the water one, there's a bit of space. In the air one, the space is increasing. Where do you think they'll pass your pencil case faster? Actually in solid. Why? Because there's no space. You're not struggling. You're just passing it. The person collects it. In water, there's still a bit of space, so it takes some time. In air, the space is actually more, because we're saying waves will transfer what? Energy from one particle to another. It is very easy to transfer because they're in contact. As compared to this, it takes a bit of time. As compared to this, you would see later on. Did this explanation make sense? Talk to me. So solid is better than water or liquid, and liquid better than air. Does that make sense? Talk to me, everybody. So that's the correct answer. So David was right by saying water, and that's how to explain. In water, in solid, the particles are, we're going to look at that in chemistry. The particles are tightly packed. In water, they are a bit loose. In air, they are everywhere. Okay. There's something I wanted to say and I forgot now. Gosh. I forgot. Okay, but it's fine. Okay, so you can draw that diagram and just make a note for yourself there. Draw that diagram. Okay. Energy is transferred quicker, or waves travel faster. Waves travel fastest in solid, because particles, please write this down, this is an exam question. Particles are closely packed together, making the transfer of energy easier. Oh yeah, I remember now. I remember. I want you to do a research for me. And I need an answer from you all. Do sound waves travel faster at night or during the day? I want you to find an answer for me. Do a research. And give me a physics answer. Don't tell me about witchcraft. Give me a physics answer. Please write down that question. I need an answer. Do sound travel faster during the day or at night? Ask AI, ask IA, whatever, just get me an answer. Yes, something.
Sound travels faster during the day.
During the
Day.
Okay, let's debate again. Who's talking to me right now? Masana.
Yeah, bro.
Okay, Masana, you said day. Zoe says night.
Day.
Day. Okay. Let's see. Day, night. Let's see.
I say day, day.
Day. Do you have an explanation for saying day? Huh? Okay, let me leave that for you to find. I want you to find out a good answer for me, physics answer, to say whether day or night. Let's quickly run. What is a transverse wave? Okay, switch off the mic. Number one, let's define a transverse wave quickly. What is this? It's almost the same as a transverse pulse, but now it's what? A wave. What will it be? I'm listening to you. All right. A wave.
Transverse is a wave in which it moves through the media perpendicular.
In which what moves? You must tell me.
Wave or about. What do you say?
What is moving? The particles in the medium. You must mention that.
Okay, the particles in the medium
The particles in the medium.
which move perpendicular.
All right. Moves
Perpendicular.
perpendicular. And if you forget the word perpendicular, what are we saying? At right,
Angle. Yeah, right angle.
at right angle to the what?
To the perpendicular
Propagation.
particle of the medium.
No, you don't use the propagation particle again. To the propagation of the wave.
Wave.
And-
Okay, this is progression.
Yeah, to the propagation. And if you forget the word propagation, just direction of the wave. And just, okay, that mic is making noise. All right, and just like we drew other end, we have that, and we have that. And this is what? Direction of wave, and the direction of what? Particles. And you can see the angle there again. Particles. And you can see your angle at 90 degrees. Please, let's draw that diagram on that transverse wave, because examiners are going to use that diagram for you. Then we define parts of a wave now. It is a succession of transverse pulses. So it's many pulses that come together to form a wave. Okay. Just 1 second. All right, quickly, let's define a few things today. We're going to define wavelength and all of those, but I want us to draw quickly. Let's draw a wave. We're going to draw quickly and then define a few good points. All right, my wave is not waving. Okay, doesn't matter how many. What is this point called? The crest. What is this point called? The trough. Hello? Somebody's talking to me there?
No, sir, it's fine.
Okay. From here to here, what do we call it? The wavelength. And we use lambda to represent it. I'm going to mark a few points here. A, B, C, D, from point B to D as well. Okay, that mic is making a lot of noise. That's also going to be, we can even have, let's call this point E, and let's call this points E and F. I can also mark another wavelength from that point to that point. I want you to see that a wavelength can be more. G, and I'm going to label this point H. We would see what that means later on. H. All right, please quickly draw that. A, B, C, D, E, F, G, H. Small letter A there. Yeah, this is a transverse wave. And then we would quickly define a few points here, quickly. A transverse wave. You can see I have it more than a pulse.
How do you know that a wave is a transverse wave or a longitudinal wave?
All right, transverse waves, we talk about the 90 degrees. The longitudinal waves will be parallel.
Okay, so just like...
And for a transverse wave, we're going to talk about the crest, the trough. A longitudinal wave, we're going to talk about. You guys are still giving me answer. All right, now guys, we're going to deal with all the calculations. We are going to deal with all the calculations. Quickly draw this. The faster we draw, the better. Okay, I'm sure we are done there. I want us to define all these important points, and we're going to start by defining wavelength. Okay, can we start quickly? all our definitions. Number one, amplitude and all of those. I want to quickly run through all of these definitions. Maybe we can get some calculations. Number one, wavelength.
The wavelength is the distance between two successive points.
Wavelength, distance between what?
Two successive points.
You're wrong. It's incomplete. It is the distance between
Two successive points in a phase.
yes, two successive points in phase. What do we mean by in phase? When we say 2 points are in phase, what are we going to say? Okay, look at this diagram. Let me quickly define in phase. In phase here, we're going to define it. Let's put it in cloud. 2 points are in phase if they occupy similar positions at different times. And when we say similar positions, let me quickly do something here. Similar positions, that is similar direction of motion. I'll give you a very good example. Please, everybody, I know you are writing. Quickly look at this with me. Look at A. Where is A going? A is going up, right? At this point. Then the wave continues. Where is B going? Down. Do you notice they are in different directions of motion? Okay. Which one is going in direction of A again? It's C. Beautiful. So A and C are in phase. B and D are in phase. So it's just a repetition of that point. So A and what? C, B, and D. Can we say E and G? Are in what? In phase. So A is replicated at C. E is replicated at what? No, I'm lying. Yeah, correct. No. E and G, correct. Because check. Down and down. So it's just a repeated point. That's what we call in what? In phase. So 2 points are in phase if they occupy similar what? Position at different times on a wave. B and C, we will say they are out of phase. Let's put the word there. B and C are out of. Another example of out of phase. A and B are out of phase. All right? Did that make sense, everybody? Because I know some of you are used to wavelength to say crest to crest. It's more than that. I can choose, if you look at it, A to C would give me another wavelength, the exact same length. B to D would give me another what? Wavelength. E to G would give me another. So see it beyond crest to crest and trough to what? To trough. Make sense? All right. Because some examiners will not give you from crest to crest. They will give you from 2 points that are in phase. And then, but they didn't give us crest. They didn't give us the wavelength in this question. We win, wah. You start fighting the examiner. But it's right there. And that's why the definition we did not say distance from crest to crest. You see, we said distance between what? 2 successive points in phase. Okay, this is the length of a wave. This is the length of a wave. What's our symbol? Measured in meters. I want to do a lot of explanation. It shows how long. It shows how long a wave is. And what is the symbol? We use the word lambda, and the symbol is like that. Lambda. Have you heard it before? Lambda. And we measure, the unit is in what? Meters. Wavelength is the length of a wave, which is measured the distance between two what? Points, successive points in what? In phase. It shows actually how long a wave is. All right. It shows how long a wave is, and the symbol is called what? Lambda. Let's go to number 2, frequency. Every time you hear the word frequency, please, I want you to think of number. Every time you hear the word what? Frequency, think of what? Number. That will guide you in knowing what frequency is. So how would you define frequency? Yes? Zoe?
The number of wave pulses per second.
Thank you. The number of what? Wave
Pulses
pulses per what?
second.
Per
Per
second.
second.
And we can also say it is the number, let me help you with this, of complete wave that passes through a point in 1 second. That passes through a point in 1 what? Second. It must be a complete wave. And that's why we use the word pulse. And the time frame is what? 1 second. 1 second. What is our symbol? No, symbol is F. What is our unit? Hertz. And it is capital H and small z. Remember here, unit is what? Meters. And we simply write what? M. Symbol is F. And we write, the unit is what? Hertz. Hz. It's the number of wave pulses per second. We move to number 3. What's number 3? Period. Guys, are we done writing? Number 3. Period. Don't think of period at school. But if you think of a period at school, let me help you again. When you think of a period, when you say it's maths period, it means during this time we are doing what? Maths. So period has to do with what? Time. Say period. Oh, so during this period we're doing what? Maths. So period has to do with what? Time. Frequency has to do with what? Number. Wavelength has to do with length. So each of those words have their keywords. Number 3, let's move quickly. Number 3, what is number 3? Period. And what did we say period has to do with? Time. So how would you define period? Not really. When you say how fast, you're talking about speed. Okay, let's see. Ntombi?
So it's the time taken for one complete wave pulse.
Thank you. The time taken for what? One complete what? Wave pulse. I want us to go back to my diagram and you tell me that the letter that shows me the period. If you go back to that wave, you want to tell me? The time taken, okay, but let's quickly talk about the symbol. Symbol is what? T. And what is the unit? Since we're talking about time, seconds, and we use what? S. Let me go back to the diagram. Tell me the letter that we can use to talk about period here. What letter would you choose? If I say which letter shows the period? A, B, C, D, E, F, G, H. Which one would you choose? I want answer from everybody, please. Let's see. Do you think it is H?
So one wave only.
Yes, period. When we say period, it's one wave.
H.
All right, you're correct. It is H because that is where my complete wave. Yeah. But I also need to know how to measure a complete wave.
5 points.
Not really.
Yeah. It's an easy way.
5 points.
Yeah, so you say, can I show you?
Yeah, come. Come show me. Show me here.
It's a 1, 2, 3, 4, 5, and the line going down. And that's one wave.
Okay.
Yeah. Let's say that I'm so that's
All right. What if I ask you to start from the crest? Where will one wave end?
Tell me, yeah.
Yes, from the crest. So let's call this, well, hold on. I just want to call this crest point X. If you start from there, where will one wave end? Where can we measure the time?
Yeah.
Great.
Red plus 1,
2, 3.
4, 5.
Absolutely. It means we can measure it from anywhere.
But 5 waves is easy.
It works.
Yeah.
It works. Guys, did that make sense to us? So don't always think the examiner would give you something like that. It's not always as straightforward as that, right? They can give you from here. Where would that be? A complete wave will be there. Make sense? All right, like you counted 1, 2, 3, 4, and 5. So anywhere could be used as a point of reference. All right, quickly. So we've talked about what? Period. Let's talk about amplitude again. We just mentioned all those amplitude crests. I'm still going to write in definition of in phase and out of phase for you clearly to see, and then we'll see if we can get one formula in today. All right, period is that. Now, quickly, a relationship between period. Before I go to number 4, relationship between period and frequency. Before I move to number 4, F is equal to 1 over T. And I want you to see something here. F is equal to what? 1 over T. What is the unit here? Hertz. Now, an examiner can ask you, what is 1 hertz? 1 hertz is the same thing as, remember this is 1 over what? Seconds. So 1 hertz can be measured as per second. Because it is 1 over S, remember? So it's S to the power of negative what? 1. You will see that in multiple choice. So if I say 5 hertz, for example, it's the same as saying 5.
So after the question,
Which unit is equivalent to hertz?
okay. So then 1 hertz is equal to?
Per second. So we just use the formula.
Alright.
The same way, we can say T, if we cross multiply, T is simple as 1 over what? F. What is this? Seconds, right? And what would that be equal to? 1 over what? Hertz. So second is the same thing as what? Per hertz. Multiple choice again. Quickly write that and we go to number 4. Number 4, we define what? We've done all the definitions, but let's just amplitude. We've done all of them before, but remember we're doing that under a pulse, right? So now we are doing it under waves, but the definitions really remain the same. Do you remember what amplitude is? All right. Maximum displacement. Maximum displacement of a particle in the medium from what? Its equilibrium position. Number 5. Like we mentioned earlier on, just to put it down, right? Crest. What is your crest? Highest. Or we can use the word what? Peak point of a wave. Yes, it could be of a pulse or I should actually use the word on a wave. Number 6. What is trough? The lowest point on a wave. I'm going to quickly rewrite the definition of in phase and out of phase. Should an examiner ask you? And then I think for today we'll just write the formula for wave speed. Next week we need to finish quickly so we can catch up with school and be ahead. I always like to be ahead of school. I love it to be ahead of school. So when you are in class, you're just revising.
I have physics homework today.
On waves. Is it easy? You've not tried it?
Not yet.
Okay, try it and let me know. Okay, quickly guys, I have just 5 minutes or so. Are we done with this page? We look at 3 more definitions: in phase, out of phase, and wave speed. Let me know, are we done? In phase, out of phase, and wave speed. Okay, in phase, if an examiner asks you, so all these definitions I'm giving you now would be what you'll be writing. In phase. In phase. Where do we say waves are in phase, or points and are in phase? 2 points in phase. 2 points in phase are separated, look at this definition, by whole number wavelengths. And I hope it makes sense. So I could have 1 wavelength or 2 wavelengths or 3 wavelengths. As long as I can measure a wavelength, that those points are in phase. Whole number what? Wavelengths. Remember, I drew that diagram earlier on. Let me just squeeze a little diagram here, because this is very important. If I have that, and I call this A, where would that be in phase again? B, C. So if you look at from A to B, what do we have? Wavelength. From B to C, another wavelength. It means from A to C, what do we have? 2 wavelengths. So if I can measure wavelength, then the points are in phase. That's why we say whole number wavelength. That is 1 wavelength, 2 wavelength, 3 wavelength, not 2.5, not 2 3/4, not 2 1/4. As long as we can measure full wavelength, then we are fine. Look, I could have another one here. If I have this D, waves goes up, comes down. E goes up, comes down. F. What is this? Wavelength. What is this? Oh, so it means D and F are also what? 2 wavelengths. It means D and F are also in phase. Does that make sense? Guys, give me a thumbs up if that makes sense. So take note of that definition. 2 points in phase are separated by a whole number what? Wavelengths. And obviously, what would this one be? Points that are not separated by a whole number. I missed the word here. Whole number multiple. Let's put the word multiple. All right. Out of phase, points that are not separated by whole number what? Multiples wavelength. And we are done. One more definition. Number 9, wave speed. Do you know how to define wave speed?
The distance the wave goes from its starting point to the end point. Measure it
Almost there. Yes, talk to me. There's a hand up. Anybody? Okay, I'm running out of time. It is the distance traveled by a point on a wave per unit what? Time. And our symbol will be what? V. And what's our unit? Meters per second. Meters per second. So we are saying V is what? The distance over what? Time. Just like we're doing in grade 8 with the triangle. Distance over time. And the distance, okay, quickly, I want us to quickly derive something here. The distance talks about what? The length. And time talks about what? The period. Let's quickly look at this math. I want to round up. This can therefore be said that over that. Wavelength over what? Time. But watch this. But what is T? What is F? 1 over what? T. Do you remember that? I want to show you all the formulas that we can use. So, therefore, I should do this on a different page. You want to take a picture of this? Yeah. Okay, quickly take a picture. I want to show you where the formula comes from and to make you see how we can put formulas together. And then we do calculations next week. Distance over what? Time. Guys, are we done writing? I'm going to steal 2 minutes from you. 2 minutes? Okay. Quickly. You're going to laugh this. I know many of you were just given the formula, right? Speed. You don't need to rewrite this if you already have it. Distance over what? Time. So V is what? That over that. And mathematically, this can be written as that times 1 over t. I don't know if you know that mathematics there. But frequency is 1 over t. Therefore, V can be written as what? F lambda. Because I am replacing this with F. So lambda times frequency. And this is the formula that you are given. But I wanted to see that I can use this to calculate speed. I can also use this to calculate speed. Distance over time, which is the same thing as frequency multiplied by wavelength. And that's how we got the formula, because we are saying F is equal to 1 over T. So take note, sometimes the examiner will not give you frequency, and you need to use the first formula. Distance over time. And our unit, whatever formula we use, our unit will be what? Meters per second. Guys, are we okay? This is going to come in handy when we look at longitudinal waves. So I'm going to start with calculations next week. Look at longitudinal waves, look at echoes. How to calculate the distance from one point to another by you using sound. Because the sound is going to bounce back on the wall and come back to you. Did this make sense, everybody? Are you okay with the first lesson? I'm sure we almost covered everything you've done so far now. Did this make sense? And for some of you, we might actually have gotten to exactly where you got to at school as well. All right. Make sure you are on the group, guys, and I'll be sharing information later in the week. That would be the end of our first lesson 1. Thank you, guys. So this is just to wrap up what you've learned so far and put a cement on some of the things you were not sure of, and give you proper definitions. Please, these definitions are proper. I'm glad you guys learned 1 or 2 things today. You learned the in phase, out of phase, wavelength. Yes, I've got a hand. Any question? You have 30 seconds. No question. Have yourselves a lovely evening. Make sure you're on the group, because I'll be sharing some good information shortly on the group. Goodbye, guys.